All right, let me talk at great length about something that I don't know a whole lot about, and that's Reynolds numbers. So this is, according to Professor Weisslogel at Portland State, right? A Reynolds number is just something that engineers use to describe flow, especially in fluid dynamics, right? And what IB is going to say is, is the flow laminar or turbulent? Okay. If it's got a low Reynolds number, it'll tend to be laminar. And laminar is just like, what we want. It's nice, smooth. The particles go in a straight line. Whereas turbulent is, like the particles are all chaotic and everything like that. And sometimes you want turbulence. Sometimes you want laminosity or whatever that is, right? If you calculate this Reynolds number, if you get something that is 1,000 to 2,000 or so, it is going to be the onset of turbulence, right? So discuss whether it's turbulent. Well, if it's above 2,000, it probably is. It's fully turbulent at 10,000. Now it is a dimensionless thing, so this has no dimensions. Somehow Pascal seconds cancels these out, and we just have no dimensions left. Okay. It is, notice that we're using the radius as one of our parameters. So this is the Reynolds number for radius. Okay, there are Reynolds numbers for diameters. There's Reynolds numbers for all kinds of things. And so really what we should be saying is it's the radius Reynolds number. Okay, all these things on the top are things that have to do with inertia, right? The dimensionality, the velocity, the density of it, right? And everything on the bottom is the viscous forces. And the Reynolds numbers get high when you have a lot of this and not much of this. Okay, and we could, I could sit here and cancel units. I think I won't do that. Let's look at some of these videos here. This is kind of fun. Passing through crystal tubes. Look at that. So this is, notice on the left side here, this thing is laminar flow right there. Here they put some helicoidal springs on there, right, to make it turbulent flow. It's also moving faster too, right, which also would give it a higher Reynolds number, right? Here they're talking about an engineering problem, right, where the speed is slow, and so the product is not homogeneously heated. So maybe we're heating this stuff. Here it's mixing it, so that's what they're kind of going for there. All right, let's look at this. This is a computer simulation, right? So you can see if you just have a tube and you speed up the fluid in there, just the viscous forces with the wall of the tube can cause these crazy, this is turbulent flow here, a model of turbulent flow. All right, and then here is another turbulent flow around a cylinder. This thing's kind of cool because when it becomes turbulent, it has actually a regime where it becomes periodic. Keep watching here. This is what brought down, of course, the Tacoma Narrows Bridge was von Karman vortex shedding. Uh-oh. What's going on here? Come on, let's skip to the good part. There we go. Oh, I missed the transition. So watch this. This wake becomes unstable. I think it's Helmholtz instability, but then again, my credentials for fluid mechanics are strictly first-year physics here. So notice this is periodicity, and if we increase the speed, I think enough, we actually will get just crazy stuff coming off of there. I don't think they didn't make it go crazy, but there it is. That's kind of cool, isn't it? All right, so let's do a Reynolds number calculation. I feel like we should, right? Let's make that a pen. Okay, water at 20 Celsius, right? It's got 1 centipoise, right? It's got this density, right? Flows down an 8 millimeter diameter glass tube. Ooh, that's gonna be tough. So our radius is equal to 4 times 10 to the minus third meters, right? Just milli is 10 to the minus third, right? Calculate the Reynolds number, determine if it's a laminar, right? What is the maximum velocity it could have and still be laminar? Okay, so evidently it's not laminar, or it's not turbulent, and then, it would be turbulent at some higher velocity. Okay, so our Reynolds number is the velocity, so 0.120 meters per second, right? And the radius is 4 times 10 to the minus third meters. And then the density is 1,000 kilograms per cubic meter. all divided by 1.0 times 10 to the minus third Pascal seconds. All right, let's calculate this. This is like the easiest question on the test. 0.12 times 4e minus 3 times 1,000 divided by 1e minus 3. And I get 480. Now my units are, on the numerator, I've got meters over seconds times meters times kilograms over meters to the third. In the denominator, I've got Pascal is a Newton per square meter, right? So that is a kilogram meter per second squared per square meter, right? Times seconds. Oh my God. Okay, kilograms goes away of the bison. Meters on the top goes away of the bison. All right, this cancels one of those. Now we have meters squared down there in the denominator. That goes away. Seconds and seconds. It all goes away. It all cancels away. It's like the end of Hamlet. All right, so there are no units. This thing has no units. It's just 480. Since 480 is less than, I think 1,000, or definitely less than, it's less than 1,000, less than 2,000, right? Then it's laminar. Laminar, right? All right, so how fast could it go and still be laminar? Let's set R to be 1,000, right? So 1,000 equals some velocity, right? Times 4 times 10 to the minus third times the density is 1,000. Notice if I make my R smaller, it could go faster. That's interesting. All right, is that right? Yeah, I think so. Yeah, I'm kind of too stupid here at the end of the day. Okay, then let's see. We're going to divide by 1 times 10 to the minus third is our viscosity. So 1,000 times 1e minus 3 divided by 4e minus 3 divided by 1,000. And I get that the velocity would be a whopping 0.25 meters per second, would make it turbulent, right? And then if it was 2.5, that would make the Reynolds number 10,000. It would be fully turbulent at 2.5, right? 2.5 meters per second would give an R of 10,000, right? Just because we'd multiply this by 10, right? We'd multiply that by 10. And that would be fully turbulent, right? But the onset of turbulence would be 0.25. All right. Yeah. There you go. Good enough.